All right, welcome back, guys. Hello. So, today we're gonna be doing sort of like a special lesson. So, because the math counts competition is coming up soon, I think you guys should be having your guys' school competitions in like within the next few weeks, I think. So, um, no, you don't have to turn on your camera if you don't want to. No. Yeah. So, For anyways, so you guys should be having your school like math counts rounds pretty soon, I would say. So we're just gonna be going over something called like the math counts like toolkit that they provide. It's just like I think it's like 2 pages, like just one page front and back of just general like formulas and stuff that you should know from like the math counts competition, right? Because generally math counts is sort of like um and like math competitions in general, you only have to know like a few number of like formulas and like general like knowledge in order to do like every single question, right? Now you might not get like the correct solution or like the correct path to solve every question, but they all generally use the same couple of formulas. So yeah, hopefully after today you guys should be pretty good going off into the math count school round. And yeah, we'll be preparing for the chapter round after that, right? Yeah. Okay, so first of all, what we're going to be talking about is prime numbers, right? So, obviously prime numbers are just like the numbers that are only divisible by themselves in one. One is neither prime nor composite. So, I know somebody who like a really good like he's really good at math and he missed like a question one on the school round because he forgot that one was not prime. So, yeah, so make sure that you remember that one is in prime. And the reason why we want to know about prime numbers is so that we can find prime factorizations of different numbers, right? So, for example, let's say we want to find the prime factorization of 437, right? Usually, if there's a number theory question that gives you some really big number, like 3 or 4 digits, your first thought should probably be to just like factorize that number. Some more people joined. All right. So, anyways, so in order to like check to see if a number is prime or not, or like if it's not prime, like what different what the different prime factors are, we have to basically just check the prime numbers up to whatever number we want to find, right? So, for example, for 437, we would start by checking 2, right? And they're like, okay, so it's obviously not divisible by 2. 3, well, 4 plus 3 plus 7 is not divisible by 3. And we keep on going until we hit a number that 437 is divisible by, right? So in the end, this ends up being 19 times 23, right? And a common question, because the goal of math counts is to do things, do questions like really, really fast, right? And um, part of that is like finding prime factorizations quickly. So we'll be going over different factoring tricks later on to like for some of our earlier prime factors. But how do we know like how far we need to go in order to um like actually make sure that we found all the factors, right? And because sometimes if the 3-digit number that we've been given is itself prime, we're like, huh, like, do we just have to check all the prime numbers up to that factor? So here's a general rule of thumb. Like we have to take roughly the square root of whatever number we're given, right? So roughly this, so 441 is like 21 squared. Maybe I'm misremembering. So this is sort of 21. So we need to check every single prime number up to 21 in order to see whether or not this is prime, right? So that just translates to everything between like in this range, right? Everything from 2 to 19. Why is this so? Because generally, let's say you wanted to factor like a square, right? So that square is like 441. Let's say we have like 21, right? And we want to list out all of our factors like this. And on this side, there's 1. This side, there's 441, right? So for every single number that's bigger than this like roughly square root term, even if it like doesn't have a square root, every single number that's bigger than this, let's say it's like somewhere over here, it's going to have to be multiplied by something that's somewhere down here in order to give you 441, right? So if we check every single number from 1 to roughly the square root of whatever number we're trying to find, um, then we don't have to check any other numbers, because we've already basically checked all of them. Because if we didn't find anything over here, then we're definitely not going to find anything over here, because it would have to be multiplied by something over here in order to get 441, right? All right. So, an exercise that I have at the bottom for this is to calculate the prime factorization of 377. I see someone's already found the prime factorization of 377. Um, so yeah. Generally, um, hmm, anyways, so generally, all of like these exercises throughout my slides, um, um, okay, so anyways, I'm gonna have these throughout my slides, right? And just like I'm gonna wait to ask you guys to like I'll give you guys time at the end to like solve these exercise problems. So try not to like solve them ahead of time. Like if you do, just send it to me in the chat, and then later on, when I ask everyone to do when I ask everyone to do the exercise, I'll like tell you if you're right or wrong, right? So just send your answer to me in the chat privately if you get it before then. Okay. Anyways, we have an important thing called parity. And parity is sort of like the beginning introduction thing to just before like modular arithmetic, right? You know how like modular arithmetic is like something that's like 1 mod 3 leaves the remainder of 1 when divisible by 3. Well, this is sort of like mod 2, right? So it's just everything that's even is divisible by 2, so it's 0 mod 2. Everything that's odd is 1 mod 2, right? So obviously, even number plus an even number equals an even number. Odd plus odd is an even and an odd is odd, right? So I bet you guys probably already know this. Sort of close to binary. Binary is, oh, the slide didn't change. Can you guys see the this slide, the one that says like I'll try exiting out and re-putting it in. Oh, all right. I'm gonna try stop sharing and resharing it. Okay, we're back. Okay. But anyway, so this is like this top table is what we were talking about. Um, yeah, so 0 and 1 mod 2 are the same thing as even and odd. Just fancier because modular arithmetic. But you guys don't need to know that. So for this kind of stuff, just use your head, I guess, and memorize this stuff. And where this comes in handy is in one specific problem type, which is this problem type down here. So right away, guys, just see if I'll give you guys a couple minutes to see if you can come up with an answer to this, and just send it to me in the chat privately once you figured it out. And I'll tell you if you're right or wrong. Try and use this, what we talked about up here. Yes, Kevin, that is correct. Good job. All right. So this question is sort of just like, um, yeah, Lucas, your answer is correct as well. Good job. Okay. So, um, okay, I'm just gonna read your username if you don't have like your actual name in. So SJ, your answer is correct. Nice. Okay. So for this question, I guess it was kind of a giveaway that it was on this slide, but basically it's just if you get it, you get it. If you don't know the trick, then you can't get it. This kind of question shows up once in like I want to say every year throughout like the levels of competition in math counts. So definitely just like know this. Yeah, so this comes up a lot, right? So for primes, the only even prime is 2, right? Because any other like even number, it's just going to be divisible by 2, and that's a prime, that's another factor besides itself and 1, right? So any other even numbers are not prime. So 2 is the only even prime. And when we look at these numbers over here, with this like 55 and this 99, we're like, okay, so this 55 is an odd number, and this 99 is also an odd number. So what added together is an odd number? We need an even number and an odd number, right? But we're given that all three of these are going to be primes, which means that one of P and Q has to be even, and the other one has to be odd, and one of Q and R is even, and the other one is odd, right? So now we just have to check, right? If P is 2, then Q is 53. And then if we plug in Q is 53, then R is 46. And 46 is not prime, so P can't be 2. So then Q has to be 2 then, right? So if we plug in Q equals 2, then we get that P is 53. And then from 53, we get that from Q equals 2, we get that R equals 97, right? So this is our only solution here because we just basically use the fact that 2 is the only even prime, and Perry did it out. Okay. Yeah. All right. Oh yeah, by the way, one thing that's really tricky, 91 is 7 times 13. I think I've been tricked by this like twice back in middle school. I think I messed up two different questions on it. 2 different years, I think. So just make sure you know 91 is not a prime number. Uh yeah, so just don't get tripped up by that one. Okay. So let's see. Yeah. So anyways, now we're gonna do some I guess like memorization things to help you do like this stuff faster. So I would recommend that you have a lot of the most common squares memorized. Personally, I would say like up to like 32 should leave you set for the rest of like competition math in general. And I would say up to like 1000 is good for a square for cubes, right? And the reason why this is helpful is because my screen changed, right? Yeah, it
Wait,
did.
so you have to remember 1,000 cubes?
Up to 1000, so 10 cubes.
Oh, okay.
Yeah, not 1000 cubes. Um, but basically, and you don't have to. It just makes things a lot easier, right? So, for example, there's been a lot of questions where I'm like, this question has a 343 in it. I'm like, oh wait, that's just 7 cubed. And now, why is this being 7 cubed important for the problem, right? And then I can actually sort of tell where I need to go for the problem from there. If I see automatically, oh, 343 is like 7 cubed, right? Or same thing with a lot of the squares here. So, in general, this is just a pretty useful trick to know. But anyways, so back to this. We are going to I'm just gonna show you guys like for any single two-digit number, there's like sort of like a neat trick that you can do to calculate it pretty quickly, right? So you just take whatever two-digit number. Let's say it's like the example here is 32, so let's just use 32, right? So 32, and then you have like three spots, hundreds, tens, and ones. So you square the first number, you put it here. You square the units digit, right? The second number, and you put it here. And then in the middle, you multiply your two numbers together and then multiply by 2. So 3 times 2 is 6, times 2 is 12, right? And then you just carry over if you need to. So this becomes 4, 2, and then 10. So 1024 is your final answer, right? Which happens to be 2 to the 10th because this is 2 to the 5th squared. But anyways, so why is this why does this work? Well, basically what we did is we just did this is like 3 times 10 plus 2 squared, and we just expanded this, right? We're like just using basic square. So a plus b squared is a squared plus 2ab plus b squared. So we squared this first one. So this is 9 times 10 squared, which is why we put the 9 in the hundreds place, plus 2 times a times b, so 2 times 3 times 10 times 2. So let's see, there's 110 here, which is why it's in tens place. And then this last one is just 2 squared, right? So this is where we get our numbers here from. And you don't have to think about expanding it like this. If you just remember that you just have to square the first one, put it here, square the second number, put it here, and then 3 times 2, and then times 2, and put it here, right? Okay. And then for a cube, for the cube, it's sort of like the same thing. I won't go over like the full expansion, but it has to do with a plus b cubed is a cubed plus 3a squared b plus 3b squared a plus b cubed, right? So what you can do here in this case is, let's say you had 12 cubed, right? You just draw out 4 this time because 10 cubed gives you 3 places to go forward to. So you cube the first term, you put it here. You cube the second term, you put it here. So 2 cubed is 8, and that's why you put it over here. And then 1 times 2. So 1 squared times 2. So 1 times 1 times 2 is 2, times 3 is 6. And then for this one, we just have 2. So 1 times 2 squared, which is 1 times 2 times 2 times 3, which is 12, right? And then we carry over again. So we have 8, 2, 7, 1. So 1,728 is 12 cubed. So I have some exercises here at the bottom for you guys to try. So just see how fast you can do these two things, and send me your answers in the chat. Yeah. Well, that was fast. Yeah, Simon, your answer to the first one is right. Yeah, SJ, it's correct as well. Yeah, Lucas and Simon, your answer to the second ones are correct. Lucas,
Too
you sent me
easy.
both of them, and they're both right.
Too easy.
Yeah. Um. So basically, I see a lot of you guys have gotten it. I'll wait a little bit more for the others. Note that this is cubed, not squared, for the second one. So for the people sending me what 17 squared is, you should be doing the cube.
They should work on their eyes. Okay. So yeah, so generally, at the beginning levels, like school and chapter round, like these earlier stages of the math counts competition, the questions will only have like one hard part, right? If you figure out that one hard part, then you solve the question and then you're done, right? So if you can do the hard part really quickly, like if you could calculate 17 cubed really fast, then you could just figure this out, like pretty then you can just figure out general questions pretty quickly, right? So first 16 squared, a lot of you guys have this memorized, so it's just 256. 16 is 2 to the fourth, so this is 2 to the eighth. If you have your powers of 2 memorized as well, you could solve it that way as well. 17, or you could obviously do this way up here. 16 is just kind of a small number for 2-digit number, so I just have it memorized. 17 cubed, you can do the same way as up here, right? So 1 cubed here, we draw our things. 7 cubed is 343. And then we have for this one on the left, 1 squared times 7 times 3, which is 21. And then for here, we have 49 times 3. Okay.
147. Okay. So this is 147, and then we carry over, right? So this gives us a 3. Our 34 goes over here and makes this a 181. And this 181, this 18 comes over here to make this a 39. And then this 3 goes over here to make a 4. So 4913 is 17 cubed. Okay.
I mean, if the numbers are this small, would it be like faster to just crunch it out?
Yeah, it could be faster to just crunch it out. If they're that small. I think the point is, if the numbers do get really big, because like the numbers in the teens, like 17, like 16, they are not going to be like the biggest numbers, right? If I ask you to calculate like 67 squared, you don't have 67 squared memorized, probably, right? So you'd
Hmm.
probably have to try and figure it out pretty quickly. Okay, next we have I guess like repeating decimals or like I guess like general decimals to fractions, right? Um I would say it definitely does help to have some of these memorized. Like 0.16 repeating is 1/6. I would say usually at the school and chapter level, it's probably just gonna give you bam, here's this like repeating fraction thing. Now figure out like what it is. Yeah, I see you realize where I pulled it from. Um, but basically, um to do these types of questions, you just label, right? So you set this equal to X, and then you take advantage of the fact that if you shift and increase like an infinite sequence up by 1, it's still infinite, right? Thanks for blocking it out, I guess. So, um, this is 10x. So you multiply this by 10, right? Because it's only one digit is repeating. So once you do this, you actually end up with 3.3 repeating, right? Because you move this decimal place back 1, but it actually ends up being 0.3333, etc. And this is just repeating on and on forever. If you move this back 1, it's just 3.3 repeating again, right? And what you can do is you can actually just subtract these two equations, right? So 10x minus x is 9x and 3.3 repeating minus 0.3 repeating, all of these threes in the end, they just like cancel out, right? Up and down. Um, all right. That's probably enough messing around with the board. Um, but yeah. So here we have 9x equals 3. And then so then x equals 3 over 9, which is 1/3, right? So this is 0.3 repeating is just 1/3, right? Okay. And then 0.16 repeating is similar. The thing is that some of these won't just give you just like 0 point and then this part is repeating, right? A lot of the time what they'll do is they'll give you some numbers that aren't repeating right after the decimal point, right? So for example, we can label this as x. So if we just try to multiply this by 10, we would get 10x equals 1.6 repeating. And if we try to subtract these, they won't exactly cancel out, but they'll still cancel out enough, right? Minus x equals 0.1666 repeating, right? 666. And these ones will cancel out, right? So 9x equals 1.5. So x equals 3 over 2 over 9, which is 1 over 6, right? Same thing. Another thing you could do is
Wait,
if
how
you
does 3/9 equal to 1/5?
where is this?
When you circle the x equals to 3/9
Oh,
equals to 1/5.
sorry. My handwriting is just kind of bad. Sorry. This is supposed to be a 3. Um, yeah. So generally we just have this is 1/6, right? If or you could just realize that 1.66 repeating is 1/3. So this is 1 and like 2/3, right? This is 1 and 2/3. And you could just combine this into a fraction that way. That works too. All right. Now for general formula. So if you just have what I said before, like 0 point something repeating, let's say you had like 2, 7, like 8 repeating, right? And I was like, okay, so I actually put this into a fraction. What's cool is that you can actually just take the repeating part, stick it on top, and on the bottom, you're just gonna stick how many nines are in this representation. So since there's 3 digits repeating, you just put it over 999. So this is your fraction here, right? The reason why this works is you just end up multiplying this by 1000 anyways, right? And then once you subtract, this part cancels out. So you just get 278 equals 999x anyways, right? So you can just take this little trick and save you some time doing these types of questions. Yeah. Okay. And um how you guys should probably I'll give you guys a couple minutes to try doing this. As people pointed out, the answer is on the left, but just see if you get the same answer as what it's supposed to be. Um while you um by I guess like multiplying by 10 and stuff, doing this trick.
If you haven't memorized, why would you need to do that?
This is just for like other things, right? If I give you a more tricky one, some of my exercise examples are, I guess, easier to help you guys get a hang of doing these.
Well, the basic point is to just cancel out the repeating decimal, right?
Yeah.
Okay, thanks.
Uh, can you turn off your mic, please? It's making a very loud rattling sound. Yeah. Okay. Yeah. So if you still got 1/12, that means that I guess you've mastered how to do these questions then. Yeah. Hmm. Yeah. So yeah, asking questions is fine. Just like don't open your mic randomly because it seems like some people's mics have like this like I guess like fuzzy interference sound. So yeah, it's kind of loud and distracting to other people. But anyways, hopefully you guys got the correct answer for the last slide. Now we're gonna go over some, I guess like divisibility rules, right? And these divisibility rules, if you're interested in any of them, I can tell you why they work. Some of these are pretty interesting, like 11, like I guess like 9 is pretty interesting, like 8. It's pretty interesting to see like why they work. So you can ask me in the chat if you want me to explain like why some of these work, but just memorizing them is fine though. So to check, I'll just go over them really quick. So to check if something is divisible by 2, you just need to see if the last digit is even, right? Okay, yeah. So for 2, you need to know if the last digit is even. Obviously, for 3, you sum up all the digits and you see if it's divisible by 3. So if I had like 111 and I was like, is this divisible by 3? 1 plus 1 plus 1 is 3, which is divisible by 3. So 111 is divisible by 3. And this is sort of like 9. You'll notice that 9 is a multiple of 3, which is sort of related to how they work. So these two are sort of similar, right? So some digits is divisible by 3 is 3's, and some of the digits is divisible by 9 is 9's divisibility rule. And then for 4, the last 2 digits are divisible by 4. So you can just chop off the rest of the number. Like if I gave you like 1, 2, 4, 7, 6, and then I was like, is this divisible by 4? You just check 76, see if it's divisible by 4. It is, so the whole thing is divisible by 4. And the divisibility trick for 4 is sort of similar to the divisibility trick for 8, right? Because for 8, it's just the last 3 digits. For 4, it's the last 2 digits, right? So yeah, that's how these ones go. For 5 and 10, it's just you look at the last digit. You guys probably already know how to do these, so I won't explain them. For 5, it's just last digit is 0 or 5, and 10 it's 0. For 6, any composite number, um you just check to see if it's divisible by its different prime factors, right? So like for 6, you just check if it's 2 and 3. And for like 15, you check to see if it's divisible by 3 and 5. As we'll see over here, 99, you check to see if it's divisible by 9 and 11. Okay. Um, and then yeah. Which one haven't I done? Okay, so 11, someone mentioned that they're not as familiar with 11. 11, it has a lot of text, but it's like alternating sum difference of the alternating sums. What this means is basically, let's say you had 1, 7, 6, 9, 4, 3, 2. Okay. So you take the alternating. So you skip every other number. So you take 1, 6, 4, and 2. So add them up, right? 1 plus 6 plus 4 plus 2 equals 13. And then 7, 9, and 3. So 7 plus 9 plus 3 is what 16 plus 3 is 19. And you take the difference, right? So 19 minus 13 is 6. Um, so this means that this number is not divisible by 11 because 6 is not a multiple of 11, right? Um, in case you were wondering, it for just divisibility by 11, it doesn't really matter what order you do this in, right? So you can choose to do this one minus the other one, or you can choose to take this alternating sum minus the other alternating sum. You don't have to spend brain power trying to figure out which one you should be adding and subtracting. But yeah, hopefully, you guys all understood my quick speed run of the divisibility rules. 11 is kind of like the most confusing, but it's also the most tested on, as you can see by this question up here. So yeah, um, I'll give you guys actually a couple minutes to do this question up here, and send me your answers in the chat when you're done. Okay? I saw Lucas, you already did it. Your answer is right. Good job. Yeah, it does. So, if you see a decimal, then the bar was whatever we saw before, they're repeating. If it's just an integer, then the bar just means that A and B are digits, right? If there was no bar, then maybe some people would think that it's multiplied by A multiplied by B, but because the bar is there, it means it's just like they're just digits in our thing.
That means you just have to multiply it by I forgot.
So all right, so this is an interesting question. Okay, so I'll start explaining now. Before we had a question in the chat though. So, yeah, Alice, your answer is right. SJ, your answer is very, very close. Um, I would double check your work. But for your question, 1.0 AB. So I'm assuming that you mean that the bar is over that you mean like 1.0 AB 0 AB 0 AB, right? Like yeah, okay. Uh, SJ, You went in the wrong direction. So, other way. We have basically for this, if you put the bar here, it sort of just serves both purposes, right? Um, you just need one bar. You don't need two bars. So this bar simultaneously tells you that this part is repeating. And I guess since it's repeating, you know that it's not just multiplied on, right? Usually the LV won't write like 1.0 times A times B. It's not really a thing that they do. So, because some people can get um confused by it. And if for some reason you come across like just a random competition, um, yeah. So if for some reason you come across like a random competition where you're just like, I don't know like what the bar means, you can probably just figure it out by context. Because in this case, it probably wouldn't make any sense for them to be divisible by, for these to be just like multiplied together, right? So yeah, yeah. So like 1.1 AB this equals like 1.1 AB 1 AB 1 dot dot. Where like A and B are digits, right? Yeah. Okay. So yeah, so other stuff like that is too advanced for this class. So we're just gonna go and do this. So here we have this number and it's divisible by 99, and we're gonna try and find a plus b, right? And for 99, we just think back and we're like, okay, 99 is 3 squared times 11, which is like just 9 times 11, right? So we split this up into 9 and the 11 part. So it has to be divisible by 9 and by 11. So for 9, the sum of its digits must be a multiple of 9. So 1 plus 2 plus 3 plus 4 all the way up until 9 plus a plus b is divisible by 9. So this part added up is 9 times 10 over 2, which is divisible by 9, so we don't have to worry about it, plus a plus b, right? So that just means that a plus b is divisible by 9. Since 9 times 10 over 2 is 0 mod 9, right? So a plus b is divisible by 9. So immediately, since you're asked to find a plus b, your answer should be like either 0, 9, or 18, because those are the only three numbers that you have two digits that can add together to make a multiple of 9, right? So that is one way you could try. So if we're trying to do this the other way, we're trying to find a and b, we can actually just go through and look at the 11 divisibility rule, right? So for 11, we just look at alternating sum. So alternating is 1, 3, 5, 7, 9, and b. So this is our first sum, and this gives us 25 plus b. And our second sum is 2 plus 4 plus 6 plus 8 plus a, which gives us 20 plus a, right? And then their difference is going to be 5 plus b minus a, right? If I did all my math right. Okay. So basically, how do we figure out what this is? Well, we know that A and B, their addition has to be 0 mod 9. And we have this. So we can just keep on trying like different digits for A and B. Basically just given that they have to add up to 9, right? So eventually what ends up working is B minus A ends up being -5, which gives us 0, right? So we have that A equals 7 and then B equals 2, right? And then A equals 7, B equals 2 fulfills both of our conditions, where A plus B is divisible by 9 and 5 plus B minus A is divisible by 11. So this is our solution. So A plus B is 7 plus 2, which is 9. Next, we're going to do sequences and series. So most of these actually, on the side, I would honestly just know this one, and this one is maybe useful if you like cool tricks, I guess. So for this one on top, this is just the sum of the first n numbers is n plus 1 over 2. Most of you guys probably already have this one memorized, so probably don't need to go into a lot of detail about it. Just there's a lot of different proofs. One way is just for any arithmetic sequence, right? It's just the number of terms times the average of the terms, right? So the average is just 1 plus n over 2, which is n plus 1 over 2, which is this part, times how many terms there are, which is n, right? So n times n plus 1 over 2 is the formula, basically, for 1 through n sum. And you can sort of do the same thing for these. This is the sum of the first n odd numbers. And if you try to do the same thing here, you would just get 1 plus 2n minus 1, which is 2n times number of numbers, which is n. So 2n times n, and then over 2, because it was this time, this plus this over 2, which gives you n squared. And then this is just the original sequence, just multiplied by 2. So you can just multiply this by 2 to get this, right? Because this is just n plus 1. Right. So generally these are just common arithmetic sequences that you'll see. In particular, this one's kind of helpful for like very few questions. For a select few questions where the question is phrased like the sum of the first n odd numbers or something. So just keep that one in mind. For a geometric sequence, okay, so this has two different parts. So there are two different kinds of geometric sequences that you'll see in math counts, right? So the first one is infinite. So it's something like 1 plus 1/3 plus 1/9 plus 1/27 plus dot, 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 right? And then let's say you want to calculate this all the way through, right? You want to calculate all of it. Well, what you can end up doing is, did you say this is like already on the other side? Because it's kind of awkward writing on the right side. So let's say this is S. You just multiply the whole thing by 3, and then, or whatever number your ratio is, right? So let's say your ratio was like 5/3, you would multiply it by like 5/3 or something, right? So, or by 3/5, depending on what way you like to do it. So here we have 3 plus 1 plus 1/3 plus 1/9 plus dot, 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 right? And you see, this is sort of like what we were doing with the repeating decimals, just with repeating fractions instead. And if you think about it, repeating decimals are just sums of repeating fractions just over 10, right? The different place digits, for example, 0.123, 123, 123, etc. These are just like 1 over 10, right? 2 over 10 squared, 3 over 10 cubed, right? So I think that's pretty cool if you think about it. But anyways, back to this. We can just subtract these off. So these will all cancel out. So we're just left with 3 over here, right? So 3s minus s equals 3. So 2s equals 3 and s equals 3 over 2, right? Pretty cool. So this sum, 1 plus 1/3 plus 1/9 plus 1/27 plus dot, 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 equals 3 over 2. Generally, I just use the formula. So it's a over 1 minus r for infinite, right? Geo series. So for infinite geometric series, a is the first term. So in this case, it would be 1. So in this case, it would be 1 over 1 minus the ratio is 1/3, right? So it's 1 over 2/3, which is 3 over 2. So you got the same thing. So this is just the general formula. You can derive it from doing something basically just the same as this. And the second one, the second type is what we have down here on bottom right, right? So for this one, it's a finite geometric sequence, right? So where we don't calculate it out to infinity, sometimes it'll be because the ratio is greater than 1, and then it'll approach infinity if we try to add like everything up. But basically for here, we just have that you can choose to memorize this if you want. Honestly, it might just be worth to memorize this, but if you're wondering, here's how you get it. So if you have a and then plus ar squared plus dot dot dot, and then let's say you wanted like n different terms, right? So your nth term, as you can see over here, is ar to the n minus 1 because you started with ar to the 0, basically. This is s, and then you can actually multiply it by r. So r times s is, I'll just shift it over here so you guys can see what's going on, plus ar squared plus ar n minus 1, and then plus ar to the n, right? So if you look at it like this, what you can do is do the same subtracting thing. So rs minus s equals everything in here is going to cancel out, and then we just get ar to the n minus a, right? Do a little bit of factoring. We get s times r minus 1 equals ar to the n minus 1. I forgot a parentheses. And then S just equals A R to the n minus 1 over R minus 1, right? And sometimes your R will be negative, which is why they switch it over here. Just multiply top and bottom by -1 to switch the signs around, right? So it becomes 1 minus R and 1 minus R to the n. But yeah, that's how this is derived. It's sort of like the same thing as how we did this stuff over here, just multiply by a ratio. Just we can't just cancel out everything over here because we still have this term that's hanging over because it wasn't infinite. So yeah, that's how you get this formula. Um, I would just say it won't come across that often, maybe like once per test max, but just keep this in mind on how to do the geometric sequences. Okay. Next, we have some different factorizations. Okay, so for our factorizations, we have just like 3 of them that we just like need to know. There are others like Simon's favorite factoring trick, if you guys know what that is. But these are just the main ones that come up like all the time. So difference of squares is a squared minus b squared is a plus b times a minus b. Sum of difference of cubes, they're all written out here. Just whenever you see difference of squares, sum difference of cubes, um, Simon is, I think Simon is like in 5th grade or something, right? Oh,
Nah.
okay. Oh, and Simon's
I'm
favorite
seven.
factoring trick? It's not our Simon's favorite factoring trick, although it could be. Um, I actually don't know who the Simon is. I think it has something to do with like I think I read it in an AOPS book one time, the lore, but now I've forgotten it. So you can go search it up in your free time if you want. Um, but yeah, so I lost my train of thought. So these ones, I would say you probably want to memorize. This one comes up all the time. A squared minus b squared is a plus b, a minus b. Like honestly, just like even if you're sometimes it won't give you a and b. It'll just give you like different squares, like 49 squared minus 37 squared. And then you can go like I can just add them, subtract them, and then I can just multiply them out, right? So sometimes it'll help you do math faster. Sometimes it'll just directly help you solve the problem. For these, I just like remembering that these are the same, right? These terms are all the same. It's just these signs switch, right? And whatever sign it is, it's just if it's a cubed minus b cubed, the negative goes first, and then this one is a plus. If it's a cubed plus b cubed, the plus goes first, and then this one is a minus, this one over here. Okay. All right. So this is like the last hump before we have some really easy things to go over. So this is the binomial theorem, and it looks pretty scary over here. Um, you will definitely have to learn this at some point if you plan on continuing on in competition math. It is useful in math counts if you get up to like the later stages. So I would definitely recommend just like if you learn it now, you won't have to learn it later, right? So um basically what the binomial theorem is you provide a way to expand stuff like this, right? So we all know that a plus b like squared is a squared plus 2ab plus b squared, right? And then some of you guys might also know that a plus b cubed is a cubed plus 3a squared b plus 3. I should write the a first here. A b squared plus b cubed, right? And then so on, right? But do you guys know about the general form of the binomial theorem, right? So the general form sort of goes like this. So we want a plus b to the n, right? So what we're going to do is we just write out our terms, right? So our first term is a to the n, and then we'll have a term that's like a to the n minus 1, and then b, and then we'll have a term that's like a to the n minus 2, b squared, and then etc. And then near the end, we'll have a term that's like a b to the n minus 1. And then finally, we just have a b to the n term, right? Okay. And then all we have to do is then plug in our coefficients, right? Our coefficients are as follows. So this is n choose 0. And then n choose 1. N choose 2. And then I didn't really give myself enough space over here. Um, oh, binomial theorem. It's called binomial because binomial means like two terms, right? So this is sort of like a binomial. If you wanted to factor out something like a plus b plus c to the n, this would be a little bit trickier. It's a fun challenge later on if you get bored to find a general form for this. But yeah, so it's called binomial because this thing inside is a binomial, I guess. So it's a binomial term. So, anyways, we have this, and then to calculate basically each of your coefficients, you just use n choose whatever your exponent for b is, basically. So, for example, here this is n choose n, and this is like n choose n minus 1, right? And then generally, if we go through and add in all the plus signs, we just end up with our final like expansion, right? And this makes sense because n choose 0 is just a 1 and n choose n is also a 1, right? So you can sort of like reality check yourself if there is indeed an a to the n and a b to the n term here with a coefficient of 1. So these must make at least a little bit of sense, right? Okay. All right, so for our example, I will give you guys a few minutes to do this. Not too much time because we need to get through the rest of this. But yeah. All right. In the interest of time, I'll start explaining. If you guys are still working on the problem, feel free to keep on working and I'll be, like I have the chat open. So if you send me an answer like while I'm still talking, I'll just like tell you if you're right or wrong, even if I'm still talking. So um basically for these like kinds of questions, this one specifically, the answer is pretty big, so it would probably be in a target round question like one of the even questions for a target round. So basically for this, you just have to realize that we're looking for the term where this one is to the third power, and then this one is to the fifth power, right? Because again, these powers have to add up to 8, and then this 2x is like just like one clump, right? This one clump of 2x has to be raised to the third power to get an x cubed coefficient, right? So to get this, basically, we're just gonna have 2x cubed and then times 4 fifths, 4 to the fifth, right? And then now we just need our coefficient through the binomial theorem, right? And it doesn't really matter which one you take because a choose 3 and a choose 5. Oh, I wrote that too close. And a choose 5 are actually the same thing anyways, right? They're the same. Um, so it doesn't really matter. Personally, I feel like you can just do a choose 3 because numbers are kind of small. So here, this is what we're supposed to get. And then if we try and calculate this out, 8 times 7 times 6 over 6 times 8 times 4 to the fifth times x cubed. On the target round, you get a calculator. I'm not gonna like calculate this out because you guys know how to multiply numbers together. But just calculating this out gives us 458,752. So yeah, quite a big number for this question. Okay, we're gonna take a break after that hard one. So here we have distance equals rate times time. So basically, some people write distance equals speed times time. Just it's basically how far you go is how fast you're doing something times how long you do it for, right? So if I'm driving at 60 miles per hour for like 2 hours, then I drove for 120 miles. So it's basically something like that. So here we have a question. If two people are making a long car trip and the first car takes 3 hours to make the trip, if the second car goes 20 miles per hour slower, but takes 5 hours, how long is the trip in miles? Okay. Um, so basically, this is just a normal distance equals speed times time question. So your distance is d. So the first car takes 3 hours to make the trip. So is whatever speed you're going at first times 3. And then the second car goes 20 miles per hour slower, but takes 5 hours, right? So times 5, because that's how much time, right? So as you can see, this is distance speed times time, distance equals speed times time. And then how long is the trip in miles? So we can set these equal to each other because both cars travel the same distance. So 3s equals 5s minus 100. So s equals 50. And then since d equals s times 3, we have 150 equals d. So 150 miles for this question. So that one wasn't too bad, hopefully. Oh, I have a lot of text on this slide for something that should probably not need so much text. Geometric mean is just you take two, it's another way of finding like the middle of two numbers, right? Or like the middle of a set of numbers. So arithmetic mean, which is what you guys have probably seen before, is for example, if I find the average of A, B, and C, this is like arithmetic mean. Geometric mean is just the same thing, but with multiplication instead. So we just have like the cube root if there's 3, the fourth root if there's 4, etc. Right? This is just here because some like math counts questions are just gonna be like, yo, like just calculate the geometric mean real quick, and you're like, okay, cool, I just plug it in, right? So like up here, what's a geometric mean of 2 and 18? It'll literally ask you this, and then you just have to know what a geometric mean is. So for here, you just take square root of 2 times 18, which is square root of 36, which is 6. Right. So very generally, it is like this. This again in math counts, you'll see questions that look like this. What is the geometric mean of these two numbers? Higher up, like in Amy, you'll see like AMGM inequality and stuff. But you guys don't have to worry about that for now. Oh, yeah. So here we just have combinations and permutations. So I would say just combinations are just the difference between the two is permutations gives you the number of ways to order a list, and combinations is unordered, right? So for example, if I wanted you to have, if I had like, let's say I had like 6 pencils, right? And I was like, okay, I have these 6 pencils and I want to like line them up in order, right? Obviously that would be 6 factorial because this first one has like 6 ways. Like the first spot has like 6 different pencils I can go to. The second spot has 5, 4, 3, 2, 1. You can think about this in any way you want. So there's 6 factorial ways. Where the second number comes in is if I only want to order some of them, right? So let's say I wanted to choose my top 3 pencils, 1, 2, and 3, right? Then I'll use permutation, right? I'll go like, there's 6 choices for my first one, 5 for my second one, and 4 for my third one, right? So 6 times 5 times 4. This fancy formula is only because people like putting things in nice and neat things. So this is technically 6 factorial over 3 factorial, but in a way it just cancels out, right? Because 6 times 5, 4, 3, 2, 1, and this 3, 2, 1 at the bottom, they cancel out. So it's just 6 times 5 times 4 at the end. So that's permutation. Combination is really important because if you see anything that says choose this from this many, you just plug it into a combination, right? And basically what this is, it's the same thing, so but without order. So let's say I said I wanted to choose 3 of my pencils, right? I'm not going to label them 1, 2, and 3. I'm just going to choose my 3 favorite pencils, right? So in this case, I would just say 6 choose 3, right? So, and then 6 choose 3. This general formula is I'm going to choose 3 pencils again, right? But this time they're unordered. So I'm just going to divide by 3 factorial, the number of things that are up here, right? And generally, the way I think about it is, for example, let's say I want to do 8 choose 4. I start from 8 and I go down how many different numbers there are is this number down here. So 8 times 7 times 6 times 5. There's 4 different things, right? And then 4 factorials on the bottom, right? And then I can like cancel out and do cool things and get 70, right? So, yeah, this is just combination. Yeah, so unfortunately, we are a bit over today already. So I'm just going to skip ahead to, this is just general formulas that you should know. Yeah, so this is the equation of a line. You guys know what lines are. Memorize this quadratic formula. It is very useful for doing stuff. I guess in general. I know people in my Calc 3 class who forgot the quadratic formula and missed points on the test. So don't let that be you. Just memorize it and just keep it in your head for the rest of however long you're going to be doing math for, right? And then this stuff for a line is pretty self-explanatory. Midpoint and stuff, you guys should all know how to do. This is Pythagorean theorem on a coordinate grid. What else? Oh, okay. So triangle inequality, I'm just speed running real quick. So triangle inequality just means that if you have a side that's really long and then you have 2 sides that are really short, you can't make a triangle because you can't close this gap, right? So how do we avoid this? Well, these 2 sides added together have to be more than the length of this side. Otherwise, you get like T-Rex arms and you can't close off the triangle, right? So generally, you have to have this be true, where the sum of 2 of your sides is more than your third side. And this applies for all of them, right? Okay. So I just actually have something important to say about the Pythagorean theorem. So a lot of you guys are like, man, this guy, Pythagorean theorem is so easy. I memorized it like 6 years ago, right? So the thing is, Pythagorean triples, a lot of these harder ones, people on tests will try to like trip you up on, right? So for example, I think there was a question, it was pretty high up. I think it was maybe question 15 on the AMCs a while ago. I think it was like 2 years ago or like last year or something, where they literally had this triangle in it, and you just had to know that it was a, you just had to realize, well, it gave you 2 of the lengths, and you just had to realize that it had to be a right triangle, right? So whenever you see some of these lengths in here, like you see a 9, you see a 40, you're like, maybe the other side is 41, right? and then maybe that'll lead you to an answer, right? So get really familiar with at least the first couple of Pythagorean triples, because I think this one, and this one come up very, very often. So yeah, just have these ones by heart. The other ones, just know that they exist, I guess. If you don't feel like memorizing all of them. Okay. You guys know how to do circles and polygon angles, so we don't have to go over them. Okay. For formulas for a cube and like different areas of things, there are a couple important things that you guys need to know. So first, for surface area. So for a cone, it looks like this, and there's two parts, right? So the first is this bottom part, which is the base surface area, and this is this pi r squared part. And then the second part is the lateral surface area, which is like the cone part of the cone, right? And this part, the formula is pi RL, right? And this L is the length from this top to one point from the side, right? So it's like this length right here. And the reason why they write it weirdly like this is because if you draw the right triangle, I can't draw straight lines, but if you draw this right triangle down here, this is R and this is H, right? So this is just gonna be square root of R squared plus H squared. So this actually just equals L. So just remember the surface area of a cone, the lateral surface area is pi RL. So yeah. Okay. And then volume, the volumes for a cone in the pyramid, don't forget to divide by 3 for these ones, right? So for a cone, just take the base times the height, divide by 3. Pyramid, same thing, base times height, divide by 3. And you should be set. A lot of people have silly these in the past by not dividing by 3, forgetting to divide by 3. So make sure you know that. And then sphere, you would be surprised at how many people, even those who are like really good at math, like enough to like qualify for Amy and like do well in the Amy and stuff, who do well in the AMCs and stuff, they like don't know like they forget the area and volume for a sphere, right? So don't let that be you. Just memorize volume and surface area for a sphere. Okay. Last slide, I promise. Okay. So the platonic solids are just solids that have the same regular polygon over and over again, and that's just basically what makes up the solid, right? So for example, this tetrahedron, 4 triangles, cube, which is technically a hexahedron, which I think is cool. So if you want to impress someone, just tell them that a cube is not a cube, but a hexahedron. So a cube is just 6 squares, octahedron, dodecahedron, icosahedron. Very important that you know what these look like, right? And how many faces each one has, right? So if you, a lot of questions in math counts will straight up ask you, like, this is a icosahedron, like how many faces does it have, right? Like it will show you a picture of an icosahedron, but it'll just be like, how many faces are in an icosahedron? And you just have to know, right? So I would recommend getting familiar with all of these. At least just memorize the faces and what they all look like their composition, right? Because you can actually just find the rest, vertices and edges from here, right? So for example, for an icosahedron, which is I guess the most common because it's the biggest, I can find the edges from just this, right? Because there are 20 faces, each face is a triangle, so it has 3 edges. So there's 60 edges, but I divide by 2 because each edge I counted twice, one from this triangle and one from this triangle, right? So I divide by 2, which gives me 30 edges. And then this gives me here, right? And then I can use Euler's theorem to figure out vertices because faces plus vertices equals edges plus 2. Also useful formula in case you guys wanted to know. But yeah, I recommend knowing generally just what these look like. But anyways, we went a little bit over time today, so sorry about that. But I hope you guys are way more prepared for the math counts competition than you were 70 minutes ago. Yeah, we're having a workshop at our local library this coming Saturday. So if you guys live near, I guess like St. Louis region, I guess, make sure to pull up. So yeah, it'll be fun. We'll be going over different problems that come up in math counts as well. So if you can make it, definitely make sure that you can come. But if that's it, then that's all for today, okay? So thanks everyone for coming today. And I'll see you guys next time, okay? Bye guys.